know how to determine the normal stress in an elastic beam, particularly subjected to the bending. For instance, okay, if you watch Olympics, you can see many of these kind of diving, okay, and basically this 3-meter diving, you can treat it as a bending problems, okay. The athlete who is standing on the plate here essentially is generate a bending on the plate. And if you ever have bent a bamboo or a stick or a spaghetti, you actually also, most of the time, if you want to break it, also you're introducing a bending, right? So what is bending, first of all? Bending actually, you can also call it flexure, characterize the behavior of a slender structural element subject to an external load applied perpendicularly to the longitudinal axis of the element. Okay, so essentially, if you have a beam, you know there's a longitudinal axis. Now you apply a load, for instance here, perpendicularly on that axis. Essentially, you bend it. Suppose this side is fixed. Okay, just like this athlete is bending a 3-meter plate. Okay, and there's also so-called pure bending. So when you apply any of your loading here, if you want to generate a bending which is called pure bending, that means the shear force is 0, which means that there's no torsional or actual load are present. Pure bending means you simply, like this panda, is apply a bending moment, okay, on the beam, and the beam is only subject to the bending moment without any other force. So bending moment, if we want to understand it more, okay, we should look at a picture like this. For all the beam we investigate, they should have a so-called neutral surface, which is or you can call it neutral plane. Normally happens in the middle of the plane, where you can draw a longitudinal axis across it. And in this neutral axis or neutral plane, when you bend it, okay, you bend it. Now we can look at this neutral axis here. You will see what happens. The neutral axis doesn't change. What I mean is doesn't elongate or compressed. So that means there's no actual deformation in that neutral plane. However, if you look at the top of the plane, now it looks like the fiber, the line here is longer than before, right? If you just compare it, and that is kind of generates a tensile stress here, which eventually introduce a tensile strain. And in contrast, if you look at the bottom part, which this kind of line here is now under compressive stress, basically it shortens after this bending happens. So this essentially gives a clear picture for bending, what happens. And there are 4 assumptions here. Number 1 is plane sections remain plane, okay? All the plane sections remain plane. And the length of longitudinal axis remain unchanged. So essentially, is the neutral axis remain unchanged. However, plane sections also you need to make sure, okay, what will mean the plane sections is if you cut a cross section somewhere here, all the section is still perpendicular to your axis, okay? This is your axis. And we assume in-plane distortion of section is negligible. So This is all the assumptions we based on, so that will help us to solve the problems. Okay, sometimes we all call it Euler beam. Okay, this is the simplest version of beam analysis, Euler beam. Euler is the famous mathematician, so we just use this name to remember him. Now, how the question is how to calculate bending stress. So it's no longer just like a stretching. You stretch it and you can use the force divided by the area. That's very simple. But for this case, not that simple. So let's approach it step by step. Okay. So to analyze a beam, first of all, you need to look at this picture. As I mentioned, there's a neutral plane. Okay. In the top, especially when you apply a bending moment, you will see that the parts on the top of the neutral plane, in this case, will under compressive stress. Okay, compressive stress. The part below it will under a tensile stress. Okay, so that the changing stress throughout the plane is very different. Okay, from a negative value to 0, and then you go back to a positive values. Okay, this is the first picture we need to know. Neutral plane, basically a layer of fibers that neither elongate or shortens in the middle. Now let's derive the beam bending equation. First of all, let's look at deformation geometric relationship. Okay, so suppose that there was a far end, we have a bending moment, and we're looking at this cross section here, and we define coordinate system x and y, z. Okay, right. So the bending at the moment is rotating against the z-axis. Okay, bending across the z-axis. Z is going through the page. Right. So suppose the symmetric axis of the cross-section is the y-axis, the downward is positive, and the neutral axis is the, in this case, okay, neutral axis, the zx. The position you don't know yet, okay? You don't know where this belongs to, okay? So neutral axis, you may know x, which we can call it longitudinal axis, and let's call it the z-axis, which will determine the neutral plane position. That is the neutral axis. So let's just now look at the even simple pictures where we just look at this side, okay, the shade area come to here. So what we should do here, right? So first of all, I would think about now you have a bending moment applied on this plane, right? And this bending moment essentially will deform the top and compressive shorten it and elongate the bottom in this case. Now we look at geometric relationships, okay? And we know, okay, there's an arbitrary place in this beam. Let's say this BB, this arc length BB, and we know at the moment the distance from BB to the neutral axis is y, okay? And we know after this kind of bending moment, essentially it becomes like a curvature, and there must be a center of the curvature, okay, assumed here. And from the center to the distance of the you know, the area you want to look at for example, BB, okay? That's called the radius of a bending curvature. In this case, rho, let's look at through the neutral axis. Okay, we always have the neutral axis as a reference. So rho is the distance from center to the neutral axis. And now we want to ask the questions. What happens for the BB? Now it's changing from a straight line to a curved line. Okay, now the arc length essentially from a geometric relationship that's equal to the distance from rho plus y. This is like the radius times the theta. Okay, theta is now the angle between these two original line. Okay, straight line here. So that's essentially the equation theta here, and you know b is here, and you know that the distance from here to here is rho plus y in this case. Okay, so we got this equation, and original distance BB is a straight line, so it's equal to the distance OO. Okay, and we all know the neutral axis, the OO wouldn't change during the bending deformation, so that should be equal to the rho. Okay, in this case, we can still use that relationship rho times theta, d theta. Okay, this tiny angle. So now kind of we have two. Okay, these two will characterize number one, this is the changed length, and this is the unchanged length. And now ask you the strain, right? Strain equal to the changed length minus the original length divide the original length, right? So the final length minus the original length divide the original length is the strain. So by substitute this equation in, now we can cancel the rho d theta, and eventually d theta can be cancelled as well, right? So once you do the arrangement, you will see epsilon is only equal to y over the rho. Rho is the bending radius. Okay, this equation A. Right. So this equation basically shows that the linear strain epsilon is proportional to the distance y from the neutral layer, neutral plane. So if y is increased, epsilon will increase. If y is 0, epsilon will be 0. Okay? Right. Let's keep going. We now get this equation A, and we take this equation, okay, and now we want to calculate the stress. So you will think, now I have the strain, how to get the stress? Right, suppose the beam modulus is known, the material is known, you use a steel to make it. Now you need to think about Hooke's law, okay, use the stress-strain relationship, because in that sense, we can simply use the Hooke's law, which is sigma equal to the modulus times the strain, and substitute that equation to here, okay? Now, what you get, essentially, you replace this epsilon with y over rho. That's the equation. Stress equal to modulus times y over rho. Okay, so this telling us what? Equation B shows that the normal stress sigma now on any point of the beam, here, at any point, this stress is proportional to the distance y, okay, from the point, for example, now you're looking at the edge area. So that point have a distance to the neutral plane y. So the stress now is reaching the maximum, right? So that's why we denote it here. Okay, on the top is negative, the fiber is under compressive loading, is shortened, so it's under compression. So we have here, and because we have defined y in the downward as a positive direction, so essentially we will try 3 different positions to see the sign of the stress. At the neutral axis, okay, y is 0, so sigma is 0. That's easy to understand. Above the neutral axis, now y is minus. You're looking at here, so now y is minus. At the same time, y minus, you substitute to b, equation b, and you get sigma is also negative, so that's why it's compression. In contrast, if it's looking at the downward part, just that part, you get y is larger than 0, positive, and sigma should be also positive, so it's under tension. So that gives us the distribution of stress across the beam. Okay, imagine that we are talking about a beam, for instance, a beam like that. Now you cut a cross section. Now in that cross section area, okay, that cross section area, you know the stress distribution is like that. Okay, we are talking about the stress acting directly on that cross section area. Okay, essentially, if you want to make it a 3D picture, you can elongate that here. Okay, that's the thickness directions, and that's the stress distributions across that. Okay, similarly here. Okay, so we'll not do that here, but if you look at 3D picture, it will look like that. Right. So now let's derive the beam bending equations. That's only give us that relationship. The question is how to get the rho. Okay, the question is how to get the rho. This is very important. Okay. Right. How to get the rho? Although we know the equation we have shown here, which is sigma equal to the modulus times the y over rho. But the rho is actually unknown. This is just something we assume that exists. So how to get the rho? So let's use the static equilibrium to work it out. Suppose still these pictures, okay? Now we just look at a tiny area of that beam at the cross sections, and we want to analyze the balance, particularly the moment balance. So you will know actually moment acting along the z-axis, right, should be the moment at the right hand side should be equal to the one in the far side, moment A. And this is essentially moment. You need to know moment is equal to force times the displacement. And now the point here is we have an area of the beam, and the force is changing at different point because the stress is varying across the section. So the force will vary as well. Force equal to, so let's say that tiny force in the small red area is equal to the stress times the small area dA. And the distance, okay, is the area between the area to the z-axis. So in this case, it's y. So let's substitute that in. So let's say a tiny amount of moment from that small area is equal to a tiny amount of force dF times the distance y. So that will equal to sigma times dA times y. Okay, and so if we rearrange it, just y sigma dA. So we are talking about how to calculate the total moment on acting on that area. So essentially we need to integrate across the area. So what we do is now we can integrate across the area, okay? Do the integrations. That's the equation C. Since we know sigma is equal to E times y over rho, and we can substitute the sigma with that part, right? So M now is become, what we can show here is, let's just substitute that FA y sigma is replaced by this term over dA. Now you have 2y, you can become a y squared, okay? That's equal to FA y squared times E over rho dA. Because E over rho, you can think about the constant, you can take it out, so essentially come to this equation. Remember, we have learned the second moment area, which essentially is, we call Ij is equal to the y squared, okay, and do the integrations. So you can compare this part. Essentially, that is the second moment area. And we can replace that term with Iz, okay? That characterizes the resistance against the bending. Now, moment equal to E over rho times Iz. And now we can rearrange that equation. 1 over rho is now equal to moment divided by EI. Right. And the rho is the things we want to determine, is the radius of the curvature of the axis of the beam after bending. And the EIZ, essentially, if the loading is given, EIZ will characterize the flexural rigidity of a beam. So if this value is high, that means it's hard to bend a sample. So now we get these equations. We know how can we denote the rho. So we have these two equations, B and D. Finally, let's say how we can get the stress itself. Essentially now we know the rho, 1 over rho can be replaced by that part. Essentially, let's just do it here. We know E times Y, and the 1 over rho essentially replaced by this EI. Okay, so what is the final result here is essentially E is cancelled. Is essentially moment over Iz times Y. Okay, so that equation tells you exactly what is the stress at any random point across the sections. Okay, I mean the cross section is always, you need to look at a cross section like that. Okay, and you apply a moment, you want to know the stress happening on this beam. Okay, it might be follow this kind of distributions. So stress will be the largest at the edge. At the center of this neutral axis, it will become 0, and then it start to increase again. Right. So what we get is these super important equations, the bending stress equations. So now if you're telling me the moment you apply, and you tell me what the shape of your cross sections, and I can give you the stress distributions across the distance of y. Okay, y is characterized any distance along that directions, especially this is a reference to with regard to the neutral axis. Okay, so this is the most important equation we should remember, and how we derive it, you need to go through it again to understand how we derive it. So when bending with a transverse force, the bending moment changes with the position of the section. In general, the maximum normal stress sigma max occurs on the section with the largest bending moment and the farthest from the neutral axis. Okay, so now we have the bending stress equations. The question is, where is the maximum stress? As I mentioned already, also from the arrow here, you can see on the edge you will get the maximum stress because y is the max at this stage. Similarly, in either intentional compression, the y will characterize the stress because moment is fixed, Iz is fixed. And sometimes we can introduce in a new term which is called section modulus, which you essentially inverse that part, these two, to Iz over y max. Okay, so then you can simplify the equation. The maximum stress due to bending will be characterized by the equation moment. Maximum moment you apply, divide by the section modulus. And section modulus essentially is related to the geometric relation, especially for different cross sections, you will get different values. Okay, this bending section modulus we can understand it from some typical sections. For example, number 1 is the rectangular shapes. We know, okay, for a given rectangular section of width b and height h, we know the I is what? Iz for this case is bh cubed divided by 12. And we know the y max should be half of the h in this case. So that's wzh over 2. That's give us the section modulus. And for circular beam sections, similarly, we know the Iz. Iz is pi d power of 4 divided by 64. And y max again is this distance. It's half of the diameter. So we get the answer. For ring-like cross-sections, okay, you have an inner diameter and an outer diameter. And we know that Iz is equal to this equation alpha. Alpha is the ratio between d over big D, okay? So you can use that equation again to work out the ring-like section modulus. Now in designing the beam, okay, how are we going to design the beam? There's many things you can do. For this case, we just look at this equation. We want to design the beam against the failure. So that means you don't want the maximum bending stress reaching the material yield strength. Okay, it has to be smaller than the yield strength. Otherwise, material start to fail at that point. So to do that, we simply just look at this equation here. Okay, we want to, okay, in this case, we want to lower the sigma max generated in the beam. How to do that? First of all, you can reasonably arrange the force of the beam so that you can reduce the value of the moments. So this moment you apply on the beam can be reduced. Okay, for example, instead of you load it for this cantilever beam, you load it here, you will generate the max moment. How about you load it here? The moment will halved. Okay, so this is kind of arrange your force of beam. When you design a bridge, you need to be careful. For example, if you have a bridge now, at the beginning you only have 2 supports, okay, and you apply a loading here, the deflection is very high, and that because the moment at the center point is very high. To reduce that moment, you can put a support in the middle, right? That's why in the bridge we have multiple supports. Okay, and secondly, you can use a reasonable sections to increase this value, the section modulus. Essentially, choose a reasonable sections, you will increase I. In that case, okay, WZ is what? WZ is the Y max, the IZ over Y max. Increase IZ will increase WZ, right? So this is essentially the second rule you can use for design. Not just look at different shape of cross sections, and if we have the same amount of area, okay, you don't change the total amount of area. I ask you how to design the beam with the largest bending modulus. So it's not easy to bend, basically. So this is actually the result. If you do the calculations, you will find I beam is the best, which with the same amount of material, you can arrange it so that you have the maximum material, okay, far away from the neutral axis so that it's hard to bend it. However, if you just make a solid beam, then that's the worst case, and it's not going to give you the best bending resistance, right? That's why, okay, when we look at the nature materials, such as bamboos, so it's so slant, so the bamboo can grow very high and very slant, but still can be very good for resist any bending loads such as the wind. And so in this case, the reason for that is it is using the kind of circular ring configuration such as the second best cross-section shape. And in our engineering, most of the time we use this type of tubes, but also we mostly use these I-section beams. That's why it is highly visible in all the engineering structures. Okay? So we will analyze some examples in our interactive sections.